Hello, everybody. So everything I'm going to tell you about today is joint with Toby Bardell, Nat Stapleton, and Jared Weinstein. So, usually in a math talk, you start with some object or question that people in the audience know and care about. And then hopefully you present some new methods and an idea for some new method how to learn about them. And then maybe it becomes a little bit more technical. I'm going to give a code talk. So I'm going to start by telling you about a mathematical object that not necessarily all of you are familiar with, try to convince you to care about it. And then I'm going to tell you about methods, but those might be more familiar because this is a conference about p-adic geometry and the methods come from p-adic geometry. So we're going to start with having some kind of a motivation. So here are a few things that appeared already in some talks. So we heard about K-theory of some ring. We heard of PHH of a ring, and TC, and TC minus, and TP. So those are things that appeared. And in the first talk at this conference, we heard about some category SH, which is presentably symmetric monoidal stable infinity category. So if you care about this kind of object, even if you didn't know that, probably you did, you care about spectra. So all of those objects are actually examples of spectra. And from this perspective, spectra is in fact the initial presentably symmetric monoidal stable infinity category that we have. So this is what we're going to talk about. We're going to talk about spectra. And what is a spectrum? So here's one way to define them. It's a sequence of pointed spaces or homotopy types indexed by the integers together with a homotopy equivalence between the n space and the loop space of the n plus 1 space. So what can you do if you have, I'll try this out. So what can you do with this collection of information? Well, if you have a bunch of pointed spaces, you can look at their K homotopy group. And because of this equivalence, that's the same as pi k of this space of loops in the next space. But what? Sorry? Is there a problem? No. Okay. So what happens when you take homotopy groups of this kind of a loop space? Well, that's the same as k plus 1 homotopy group of x n plus 1. And for example, if you're not familiar with this, right, the connected components of the loop space is loops up to homotopy, so that's pi 1. So what that means is that, in fact, this group depends only on the difference. So we can define the homotopy group of the spectrum to be pi k plus n of xn. And this definition does not depend on n at all. Right? So what does that mean? Well, it means that this definition makes sense even if k is negative. Because if we take k to be minus 100, we can take n to be 1000, and that would make sense. And also, we can always take n large enough so it would be in a billion. So those are a billion groups, one for every k. And the example above, so when we're saying something like the ith k group of K, what we mean is actually the ith group of the spectrum KR, and etc. Okay, so this is what I call a politeness definition. I'm not going to use this definition at all. It's just impolite to start talking about objects without defining them. But it's not going to be used at all. So, and the reason that it's not going to be used because this definition, although it's very quick, it is actually kind of hides the main tuition we're going to be taking while thinking about what spectra are. So, so spectra are extremely ubiquitous. They, as you can see, appear in K-theory and p-adic Hodge theory, but they also very important in algebraic topology and in differential geometry and in they appear in representation theory. So they're very ubiquitous. And one way to explain why is the following analogy. So spectra are to spaces, and by spaces again I mean homotopy types or anima, for whom prefers, are the same as abelian groups are to sets. That's so we want to think about spectra in analogous fashion to abelian groups in the world of homotopy. And this analogy is the one that's going to guide us. So if we think about abelian groups, abelian groups are extremely useful, of course, and they're also kind of the bedrock of doing algebra. And rings, for example, are abelian groups with multiplication, etc., etc., and those are multilinear maps. So when we think about abelian groups, we don't want only linear maps; we want multilinear maps. And the fact that you can do this encodes by the fact that you can tensor abelian groups. And this is the symmetric monoidal structure on this category, and it has a unit, the integers, and again by analogy, spectra also have a tensor product, sometimes known as a smash product. And there's also a unit called the sphere spectrum. And for example, the homotopy groups of this sphere spectrum are what known as the stable homotopy group of spheres in algebraic topology, and understanding them is one of the big motivating problems in the field. But in any case, we have this big category, and all of those examples over there live here. So what's the
Classically, it would have been best to the dependent model with this definition of spectrum, because you have to make a choice. I mean,
that's it's true, but we don't live in classical times anymore. Yes. So getting a good framework to work with those things was not an easy thing. And there were a lot of people who worked on it, and nowadays most people use the language of infinity category in this context as developed by Jacob. So where are we? Okay, so yes. So how would we study this kind of objects? I think I failed with what I was trying to do. Never mind. So how do we study spectra? Well, how do we study abelian groups? So, one basic idea in the world of abelian groups is that is primary decomposition. If you want, you can say the following thing. If you want to impress people in a fancy cocktail parties, you can say that abelian groups are nothing but quasi-coherent sheaves on spec Z, and spec Z is this funny space that has one generic point and one point for every. So so why is this fancy longer name helpful? Because it suggests a way to divide and conquer the problem. We can think about abelian groups locally around each of those primes and then glue the information back together. And that's that's a very helpful. So for example, you could have, choose one prime p and think really a lot about geometry around this p and do a conference about that. So we want to do a similar decomposition in the world of spectra instead. And for this, you need to think about, what would prime constitute in this context. And one good way to think about the way you see primes in this context is by thinking about residue fields. Primes are classified by residue fields. So there's the residue field Q here. There's a residue field F2, F3, etc. And you can try to classify possible residue fields in the world of spectra. And when you do that, you can come up with a reasonable definition. And then Hopkins, Evinat, and Smith told you what the answer is. And you find there's way more primes. So all the primes that you had before have this name infinity attached next to them. And then kind of somewhere between this prime and this prime, you have a prime called 2, 1. And here you have another one called 3, 1 and 5, 1, etc. And then a little bit closer, you have a prime called 2, 2, 3, 2, 5, 2, etc., etc. Okay? And so you have this. And those are the different residue fields, the different primes that you can decompose every spectrum into pieces this way, and then maybe try to glue them back together. The residue, we're going to do something, which is we're going to fix a prime, P, and work only in this prime. So we're going to think about what happened when you think about only just one prime, one classical prime, I mean, now. And it's just going to be easier to describe. And we're going to ignore, so we think about this family of primes and going to ignore what happens outside of it. And the residue field at Kpn is called Morava-K theory. So it's a spectrum. It's a ring in the world of spectra, which plays the role of a residue field, and it's denoted by Kn. And the prime P is suppressed because we chose it and fixed it for the entire talk. So usually we don't put it in the notation. Questions? So our approach to understanding spectra is to understand it at every prime separately and glue it back together. And this approach to spectra is known as chromatic homotopy theory, because as you can see, the different primes has different colors. So what do I mean by decomposing it to pieces and glue them back together? We have an abelian group. We can p-complete it. And p-completing an abelian group is approximating it universally by an abelian group that is constructed out of extensions and limits by FP vector spaces. And we can do the similar thing here. We can define a category called the Kn local category, which you should think of as the analog of p-complete abelian groups, which are those spectra that you can construct out of limits and extensions out of Kn modules. And similarly to the way that if you have a general abelian group, you can p-complete it, there's a functor. This inclusion has a left adjoint, which is Kn localization. So that corresponds to kind of completing around, if this is Pn, completing around kind of a small area here. There's another process you can do, which is you can consider things which are constructed in the same way out of extensions and limits, out of modules, out of each of the primes from 0 to n. So you can consider the category of bigger than that is the category in which you consider all of those residue field up to 0. And this also has a localization. This is just denoted by L, denoted by L more equal than N. So the idea is to use this as successive approximation for spectra. And this doesn't always work in the sense that this way to approximate spectra, decompose it and glue it back together, sometimes you don't get what you started with. Some information can be sometimes lost. But there's a theorem by Hopkins and Ravenel called the chromatic convergence theorem that says that if you take something like the sphere spectrum, which is the unit and one which we're very interested in, and let's say you p-localize, by which I mean you invert all primes other than p, which we do anyway, this is the limit of taking L more equal than N of this sphere. So it's some way to break up this thing into pieces which are more manageable. And now the difference between two consecutive pieces. So right, so universally approximating, so if we have the sphere, right, universally approximated by everything up to N is definitely better approximation than approximating it by all the things up to N minus 1. So in some sense, a strategy to understand this is to understand the difference between those two. And this is a pullback, and you can put it in a pullback square by considering, so we have up to Pn minus 1, and we have the information around N, and this is, and there's an additional piece which is a gluing information. So you can think about it. You have a closed locus, which is this guy, and you have an open locus, which is everything outside, and you have to glue along the tubular neighborhood. That's this. So this is the chromatic approach to understand spectra. So the entirety of the results that I'm going to tell you today are concerned with this object, which is kind of the associated graded piece. And if we have time, which I'm not sure we will, maybe a little bit more generally this category.
What about you said that infinity also gives you a prime to some extent.
So in some sense, its contribution in the case of the sphere kind of goes away. Doesn't. Yeah. I'm saying something soft because, but that's the formal that I just said is the formal state.
But the rough traces for which p-local, for which all LS are equal to N are 0 and they are not 0.
Yeah. So you can so every abelian group is in itself a spectrum. So you can think about FP itself. All of those guys are going to be 0. So definitely that's not a complete general. Okay. So the object we are going to concern ourselves with are that's it. Okay. The object we're going to concern ourselves with is this K-local sphere. Let me tell you a little bit about it. So we have 1 for every height, and the prime is, as I said, fixed. And so the 0 local sphere is just, if we look at the homotopy groups of the K0 local sphere, this is just Q when star is 0 and C0 is otherwise. So that's a very simple thing. What about the pi star, the K1 local sphere? So this is very well understood. And just for writing simplicity, let me assume that P is odd, although the answer is also known when P is even. It's just it's going to be take longer to write. So the p-adic when star is 0 or minus 1, and then it's 0 if I is different than 0 and I is not, and I plus 1 is not divisible by 2p minus 2. And then it's z mod p to the k, where k equals the valuation of I plus 1 divided by 2p minus 2 plus 1 otherwise. So the precise formula is not of that big importance for us today. There are only kind of two things I want to mention here. One of them is that you see most of it is torsion. In fact, there's only two homotopy groups which are not torsion, degree 0 and degree minus 1. And the other thing is that we have a very, well, this is a fairly simple formula. It might take a moment to read it, but it's very concrete and understandable. There's a very clear pattern going on. So this is by now fairly classical, and I guess due to Adams, I think, in that form. Okay. So what about the K2 local sphere? So I'm not going to tell you what the homotopy groups of the K2 local sphere are, because they're just a terrible mess. It's like you can go in and read papers about it, and the answer takes pages of pages of pages to describe. I will mention names of some people that contributed to the computation, which is now known. So Baudry, so those are several different papers, and then Baudry together with Gors and Hen, and then Gors and Hen and Mahold and Rezk. And then there's a paper by Mark Burns, and there's a paper by Shi Momura Yabe, and there's a paper by Lada, Paul Hasse, and then Hannigan together with Karamanov and Mahold again, and there's and Popova. Okay, so this is my attempt to do justice to the amount of work that went into doing this. But if I wanted to tell you what the answer is, it will take the entire time of the entire talk. It's like complicated homotopy groups flying around. And then when we're asking this for n bigger than 2, then it's a big question mark. Okay? So, the fact that as hard as this problem is, the fact that the answer is so hard to describe suggests somehow that, maybe we can ask a question that zoom into some pattern that we can kind of describe more universally. Because, there's like, sometimes the methods are hard, but sometimes the answers are hard, right? And this is kind of doesn't bode well for higher heights. And you can try to tensor with Q. So if you tensor with Q here, you just get Q. And if instead of taking P local sphere, you take the P complete sphere, you're going to get a QP. That doesn't really matter. This is just for some symmetry, I'm saying it. If we tensor this with Q, we're just going to get a QP and a generator in degree -1, so an exterior algebra on a generator in degree -1. And if you look at what people did here, and you rationalize, you're going to get it after rationalizing, you're going to get QP and 2 generators, 1 in degree -1 and 1 in degree -3. And that's it. So, so here there might be a chance to say something. That's what we want to do. You want to say something? I'm going to use other boards. That's what I'm going to do. Okay. So our first goal, and probably given the time that I'm doing here, maybe our only goal for today, but we'll see, is to compute I star of the K-n local sphere rationalized. And in fact, you know, here's a very, very naive guess, if you want, that comes up from the 3 examples that we have. It's a QP algebra with n generators, 1 degree minus 1, 1 degree minus 3, when the last one is degree 1 minus 2. So, in fact, the theorem we will prove is that this is in fact correct. Okay, so this is the theorem.
Why did you draw a circle on that sphere?
I'm sorry?
The circle on this.
Laziness. Okay, so this is our theorem. Okay. So how would you prove such a theorem? And maybe, you know, and how would you do these things as well? Like how do you approach the homotopy groups of the K-n local sphere? So if you remember, I mentioned before, trying to impress you, that abelian groups are quasi-coherent sheaves on the spectrum of Z. And this is a way to think about quasi-coherent sheaves by decomposing them according to the Zariski topology. But there's a finer topology that one can consider, which is very useful in algebraic geometry, which is the Proetale topology. You know, working over a local ring or over a field is easier than working on over an arbitrary scheme. But if you can take things to be algebraically closed, right? If you can do Galois and Proetale descent, things becomes even simpler. So that is indeed the way that those computations go. So it turns out that this K-n local sphere, I'm just going to stop doing this 0. It's just that I broke my leg, so I'm trying to save energy. Has a profinite Galois extension called Lubin-Tate theory or Morava-E theory with an explicit group Gn acting. And the way that those things are being attacked is by using descent along this Galois extension. So let me be a little bit more concrete with this. So first of all, what is this mysterious group Gn? Well, consider a division algebra over QP of invariant 1 over n. Gn is just the profinite completion of the units. Okay? What about this En spectrum? So I'm not going to define it, but I'm going to tell you what its homotopy groups. We understand those fairly well. The homotopy groups. So first of all, this is what we call an even periodic spectrum. So the homotopy groups are just pi 0 join a generator in degree 2, which is invertible. And pi 0 is also understood. It's in fact the Witt vectors of FP bar join U1, UN minus 1. Those are generators. And this isomorphism is not canonical. It's the way you should think about this ring is in fact is the Lubin-Tate ring. So that's canonically identified with the universal deformation ring of a formal group of height n. And the approach, the existence of this Galois cover give us an approach to compute the homotopy groups of the K-n local sphere via Galois descent. And computationally, that comes up in the form of a spectral sequence. So take the cohomology of Gn acting on pi t of En, and there's a spectral sequence converging to pi t minus s of the K-n local sphere. This is known as the Devinatz-Hopkins spectral sequence. So the good news is that this is a fairly mild group, right? It's essentially very close to be some kind of a finite dimensional p-adic Lie group. And this is in some sense a very mild ring, like it's a, you know, a local, complete local ring. But the action is extremely complicated and very hard to understand. And in particular, those cohomology groups, there's not that much which is known about them. And well, at the case n equals 1, this is just the group ZP star, and this is just these Vit vectors. So I'm sorry, QP star. And this is just the Vit vectors. So we're really in a very simple situation, and the computation is fairly easy, and this is how you get this. In the case n equals 2, it's much harder, but things are somehow known in an explicit enough manner to get some control that allow these computations. But for higher heights, this is somehow severely complicated and not well known. Nevertheless, this is the approach we're going to take, and we're going to hope that after rationalizing, we can make our life much, much simpler. Questions? Okay. Yeah. Okay. Okay. So let's start to simplify the problem to some extent. So the nice thing is that because this is a compact p-adic group, rationalizing goes inside. So in fact, we get a spectral sequence from this, what is known as the Morava stabilizer group, acting on the T homotopy group of En, rationalized, converging to the rationalized homotopy groups, the K local sphere. And a lot of this goes away now, because inside this group D star, we find that we have QP star at, and in it we have ZP star at. And even though the action of this B group is hard to analyze, this smaller subgroup, which doesn't need to be profoundly completed, its action is very easy to understand. On pi t, so pi t for odd is 0, and on pi 2t, this acts as the t power of the identity character. So it acts trivially on pi 0, acts by and the number a here acts by multiplication by a on pi 2, and a squared is pi 4, etc. So we have a normal subgroup, which is a normal cyclic subgroup which acts with a non-trivial character on all t's which are non-zero. So that means that the cohomology has to die. So in fact, we can just write 0 here, and this spectral sequence becomes an isomorphism. So the rationalization of the K local sphere, there's no spectral sequence anymore. It's just the cohomology of this Morava stabilizer group acting on the rationalized Lubin tetrane, and nothing more. So now we are definitely completely in the realm of some kind of algebra. There's no, in some sense, the homotopy information has now been taken away. So, yeah.
So those groups are profined, and the homotopy in question is kind of continuous modular.
Yes, everything here is everything, yeah, absolutely. Yeah. So, also before this also. Okay. So as the old song says, what does p-adic geometry has to do with it? Well, how can we think about this pi 0 of En for this context? Well, there's a regional analytic space. It's the open polydisk, but kind of canonically identified with the regional analytic fiber of the deformation problem for a height and formal group, known as the Lubin-Tate space. So this is some regional analytic space of dimension n-1, and the bounded by 1 functions on it are canonically identified with the Lubin tetrane. Furthermore, there's an action on this space by this group Gn And the corresponding action on O plus is indeed the action we're looking at. So we are actually seem to be looking at the cohomology of this group acting on the bounded functions, maybe up to rationalization. So, as I said before, right, where did we get this spectral sequence before? We got it for Galois descent. So it stands to reason to say, oh, maybe we can think about this geometrically as some kind of a Galois input to a Galois descent spectral sequence, but this time not in some homotopy spectral way, mysterious, but just in the world of p-adic geometry. So this action of the Morava stabilizer group on this open polydisk, you can't quotient it. It's not a free action, if you will, but you can look at the stack. So you can construct a stack, which you get by taking this quotient, and you can suggest an idea. Maybe, maybe this, so this is what we're trying to understand, right? Well, this is the same as O plus of LT. So maybe this is the input to a spectral sequence that converge to the cohomology of LP mod Gn with coefficients in O plus. Now, the nice thing is that if that would have been true, well, faulting's proved, and in the form that we're actually going to use it, it's a theorem of Schultz and Weinstein, that this stack here has another description. It can also be written down as another p-adic space called the G-field upper half space, quotiented by an action of GLN ZP. Okay. So this space, what is it? It's a subspace of the n-1 projective space as a regional Lich variety, and you remove from it all QP linear hyperplanes. And the GLN-ZP action is just the one that you have because of projective coordinates. So because of the Schultz-Weinstein isomorphisms of stacks, this can be reinterpreted like this. And now, maybe we can write down another spectral sequence, this time with O plus of H. And what is O plus of H? Well, this is a p-adic analog of the upper half space. So a version of Liouville's theorem tells you that the bounded by one functions are just the constant bounded by one. So this suggests that the thing that we're trying to understand is isomorphic to this thing. Let's try to understand what happened after rationalization. After rationalization, this thing is the cohomology of GLN-ZP and coefficients in QP, which already appeared today. And this is this. So if we could have claimed that those two question marks are correct, we would be done. Unfortunately, you can probably guess, because I used the color red, which is the scariest color, that both of those things are false. So how do you prove the theorem anyhow? Well, let's try to understand how far is this from being true. And we can hopefully show that this is far from being true in a controlled way. Controlled enough that we can still prove the theorem. So what kind of spectral sequence we do have, right? Like there is such a thing as descent for stacks. Well, what kind of a stack is this? This is a Proetale stack. So what you have is a spectral sequence with a continuous cohomology of Gn acting not necessarily on O+, but rather on OQ, HQ, Proetale, of the Lubin-Tate space with coefficients in O+. And then this would converge to S plus Q. Note that where Q equals 0, this is exactly the Galois section. So if I would have known that on the Lubin-Tate space, O+ is the cyclic, its cohomology, the Proetale cohomology is 0 for positive Q, then this argument would have worked. But it just falls. Okay, so our goal is to understand the Proetale cohomology on O+, and once again, hopefully understand to what extent it is not true that it's a cyclic, and the same statement for H. Right, so we need it on both sides. Questions? This is very stupid. I shouldn't do it with a broken leg. That's definitely. Questions? Ofer.
Nobody was going to come help you.
Okay. So our goal is to understand HS, Proetale, LT, or H, O+. That's what we.
The question, of course, whether it makes sense, like if you have to use a naive notion or a condensed notion or something like because sometimes things are not separated, and then it's tricky to define what you mean by this cohomology, this coefficient, something. So.
Indeed. Yes. So I need to get this as some kind of a topological module, and the best way we know how to talk about topological modules is using it as a condensed abelian group. So I need to compute this not only as an abelian group, but rather as a condensed abelian group. That's right. I wanted to ignore this point, but I should have known that if you're in the crowd, I can't ignore any point. So it's okay. Now I'm going to ignore this point. Okay. So this is what we want to understand. Okay. What happened when you compute the Proetale cohomology of O+ and then rationalize? And should we expect it to be just H0? Well, here's a those are big regional analytic spaces. Let's start analyzing this in the case of a point. So what can we say about Proetale cohomology of SpaqUPO plus rationalize? What can we say about that? Well, what is this thing? In this case, we know what is we know how to descend, right? We can take CP, and O+ of OCP is OCP, and then we can descend down. So this is just a cohomology. If you want, this is just a cohomology, the continuous Galois cohomology of QP acting on OCP, and then rationalize. Now, once again, this is cohomology with respect to a profinite group. So this is the same as the continuous cohomology, Galois cohomology of QP acting on CP itself. And this was computed by Tate, and this is just QP, where S equals 0 and 1, and 0. So even for the point, right, this is not a cyclic. I have O plus itself is of spa QP is QP, but I have an H1. I have some, so this thing is an algebra, at least after rationalization, is QP adjoins some epsilon, which is a degree 1 element, right? Well, what can we do now? Well, you know, it's like, you can ask, well, does every polynomial over the reals have a root? No, for example, x squared plus 1 doesn't have. Okay, what happens when we add this root? Now it works. So can we, like, let's do this. Let's add the minimal thing and see if it works. So this guy, right, admits a map. Or so if you think about this as a graded thing, this thing admits a map from O plus LT, right, just by the 0 level. And it also admits a map from the answer for spa QP. Because this leaves over spa QP. So it admits a map from the transfer product. Now you can ask, well, is this an isomorphism? Yes, this is an isomorphism, and the same thing is true for H. So it turns out that even though it's not true that we only had H0, the only thing we have is another copy of the same story over H1. And that's enough to show that you have to have the same answer on both sides, because it's just duplicated. So the technical heart of the paper is doing this. It's proving this. So let's say, how do we do this? How do we prove such a result for LP and H? Any questions so far? Okay. So let me start by convincing you that that's probably a reasonable thing to expect. No, I did it in the wrong one. Oh, did it. Okay. So here's why it would be a reasonable thing to expect. So let's pretend for a second that what we had here was, you know, that LT was quasi-compact, okay? Which it's not. But let's for a second pretend that it was. Well, then I could take the tensor ring with Q inside. So I would get that I'm trying to compute the Proetale cohomology of X with coefficients in O. Now, X is some bridge analytic space over QP. So I can descend down after taking base change to C. Essentially what I did here for the point, but geometrically. So I have a spectral sequence going from the, again, QP Galois continuous cohomology of the Proetale cohomology of X base change to C with coefficients. Okay. Let's proceed. But according to a result of Batmore and Schulze, this thing is identified with differential forms, appropriately twisted. Now, as long as Q is positive, we have here essentially some infinite thing modeled after the twist, the minus twist of CP. And in fact, this result by Tate more generally is that this is equals this 12 fingers of Q0, and it's just 0 otherwise. So this means that all this interesting Durami information, I don't know, Hodge state information that you have in this Proetale story is completely killed by the Galois cohomology because of the twist. So the only possible contribution is for the cohomology of H0. But then we get exactly this phenomenon. We have something CP linear, and it's just duplicated by the same reason. So that shows that in this case, we have the desired isomorphism. Of course, this is not our case, because neither H nor is the Lubin-Tate space are quasi-compact. So this is not going to work. But we're computing cohomology. So there's a very natural thing to do, which is to cover our spaces by quasi-compact opens and try to get this result by descent. There's only one subtlety with this plan, which is, so if I would have claimed that this is an isomorphism without tensoring with Q, let's say, or giving you this kind of a natural formula without tensoring with Q, and I would prove it for every quasi-compact, and then I could descend. But that's not what I said. I said that this is so true after rationalization. So it means that I'm claiming this statement up to that this is an isomorphism up to torsion. When I have something which is covered by infinitely many opens, for example, like LT or H, if I don't know that the torsion is bounded, it's possible that when I'm trying to descend, the torsion going to conspire on different opens to give me non-torsion information at the limit. So if I want to use any kind of descent argument here, if I want to do any kind of a local global argument here, I'm going to have to do an integral version of this, and I'm going to have to claim that for some family of covers, I would know that the cofiber is bounded torsion by some universal bound. So that's the structure of the proof. Instead of doing things for O, we're doing them for O plus, but we don't have to do it precise. We're allowed to do it up to torsion as long as we know that there's some universal bound on the torsion that appears in our computations. So now the question is, well, okay, for what kind of quasi-compact opens, we have an analog of this result, which is good enough to get a bound on the torsion on one hand, but on the other hand, is enough to cover the two spaces we care about, LT and H. So let me answer that. Any questions?
The Lubin-Tate is just a disk, an open polydisk.
Yes.
So it's covered by things which over C are the same, but over theta are not.
That's exactly right. So that's going to be a subtlety that's going to influence the argument in the next 6 minutes. Okay. So there's essentially a version of this statement that we're going to want to use. And this is, so it would be interesting, I think, to have like a very general result, but we found some kind of a, so the next step is kind of technical, right? So we found something which is good enough, and the extent to which this can be used for more general spaces, I think is, I don't know, I think is interesting. But for us it was enough. Okay. So yeah. Yeah. So what do we? Wait. So how much time do I have? 5 minutes. Okay. Then I'm gonna have to jump over this. Okay. So Okay, maybe I'm going to jump over this next step because I have only 4 minutes. So the cover that we are, maybe I should say, oh sorry, making the recomputation and as we yes. Okay. Okay. So let me not get into the exact way we do it. Let me just say that the collection of spaces that we consider as our basic versions of this result is formal schemes. Is a fine formal schemes that admits a semi-stable model after a tame extension, and for those family we can give a bound, and those are enough to cover both the Lubin-Tate space and the Driven-Hopper-Raff space. So the Lubin-Tate space, it's covered by closed disk, and indeed they're not the same over QP, but they are this, but they do have formal models, semi-stable formal models after a tame extension, and then for the Drinfeld upper half space we use the Grosser-Klone model to cover it. So that's those are the two things. So in the last 3 minutes, let me
There was a formal scheme of the Lin of that. It's the same for Drinfeld upper half.
I admit that I don't know the history of this. So
there was some old notes of the it's in some paper of the 7, you know. It's just constructed Swiss, but it's the same.
okay, so what I wanted to say, well, okay, I think I kind of misplanned the last few minutes, but never mind. So what I wanted to say is just that there are other questions in the scan local world that are generally approached using this descent, and it seems to us that it can be fruitful to try to use this to translate more problems from one side to the other, and that's yeah. So and anyway, yeah, I think I shouldn't declare anything in 1 minute. But my point is that somehow there's I think it's a general thing, and we're hoping that people who are interested in p-adic geometry would be interested in collaborate to find more ways that this kind of methods can be used to answer questions in chromatic homotopy theory. Let me stop here.
For those who know nothing about what you're talking about, can you summarize what you proved using this p-adic theory? And
what is the result in
what was the conclusion about homotopy groups?
So there are those K-n locals. There's this K-n local sphere, which I don't think you were here when I defined.
I was.
You were. Okay. So we proved. Well, you were. So we proved that if you consider the non-torsion information, that's just an exterior algebra on those.
The point was on tensoring of Q, you were able to answer for every n.
We know it for every n. Yes, that's the point. And the answer is both can be written on the board and is now known. Yes. Other questions? Yeah.
That's another stupid question. Like, if you run now the chromatic convergence, I mean, everything's supposed to die in the end again, right? I mean, you have all these K-n local classes that are supposed to not contribute in the end to the rational sphere. Will that happen?
So we don't know exactly how it happens, but there's a conjecture known as the chromatic splitting conjecture, which is the simplest way that it can happen. And that one essentially says that well, okay, I think it's going to take too long right now to write all the long exact sequences, but essentially those disappear kind of immediately in the simplest possible way. But
what happens if you take this information and takes the ln-1 localization and less than equal to n-1 localization of this?
So the ln-1 localization of the Kane local sphere and the Kane local sphere. So okay, so if you take the chromatic square, sorry. If you take this square and rationalize it, okay, we know what happens, right? So you get Q, and then Q, and then, well, this twice, this thing twice, and an isomorphism. So in that sense, those things disappear immediately. They are the same here and here. Nevertheless, you can ask, you can look at the fiber of this map and ask how complicated is this map. The simplest possible thing that can happen is it will split, and that is not equivalent, but that would predict this picture. So there's this is evidence to what is known as a chromatic splitting conjecture.
I understand the transition maps are the ones we expect. Epsilon go to the epsilon, and the last one goes to 0.
Which transition maps?
No, for this,
No.
maybe there is no transition. This is not ln, it's kn.
It's not ln, it's k.
Okay.
ln doesn't have any rational information outside of pi 0. ln doesn't have any rational information outside of pi 0 because ln is what happens if you restrict between 0 and n, right? And rationalizing is the same as restricting all the way here. So if you, this is like an open substack. So you restrict and you restrict again, it's just the same as just restricting immediately. So rationalizing ln is just L0. However, Kn is like the completion along this closed locus. So it intersects all the open loci. And that tells you the way that it intersects. This is from the geometric point of view, this is the gluing data, or part of the gluing data. It's only the gluing data between n and 0. And if you want to understand this square, we want to understand the gluing data between n and n-1 and n-2, et cetera, et cetera. And well, this is a piece, the first piece.
Okay, so the question was to explain. So what? Maybe I misunderstood the Schultz's script. So because
I think Peter asked somehow in what way everything conspired to disappear. And what I'm saying is it disappears kind of immediately, but it tells you something, it still tells you something about the way that things glue, or some part of it. On the level of homotopy groups, this map after rationalization is an isomorphism, so it doesn't influence the difference between those two. So there's, okay, so I can say so one thing that you would want to understand is what is the n-1 localization of the Kn local sphere, right? That's something that would be good to know. So the conjecture is that this is, so let's say P is odd. So the conjecture is that this is a copy of the n-1 sphere, and then you add a bunch of exterior pluses as before, but epsilon minus 1 minus 2i is kind of supporting a copy of the n minus I sphere. So what does that mean? So for example, it means that if you take L1 of the K2 local sphere, so what are you going to get? You're going to get a copy of the L1 local sphere plus another copy of the L1 local sphere plus plus a copy of the L0 local sphere plus a copy of the L0 local sphere, when this lives in degree -1, so suspension -1. This is suspension -3. This is like the product. It's suspension -4. And now if you take L2, so this was verified. This is known. If you take L2 of LK3, the conjecture is that you're going to have 2 copies of L2, and then you're going to have a copy of L1 and another copy of L1, and then 4 copies of L0. Which is like, they behave like exterior algebra, but every generator lives in the smaller open part of the stack. And if you rationalize, you can't tell the difference anymore. So the expectation is that you're just going to get an exterior algebra, which is indeed what you get. So in that sense, this verifies what is known as the chromatic splitting conjecture, but doesn't prove it. Other questions?
Okay, so no more questions. So the next talk is tomorrow at 10 in the morning. And let's thank the speaker again.